Hi, everyone. So yesterday we finished the topic of low degree testing, and today we're going to talk about some rather new protocol from only 3 years ago, something like that, which is called the FRI protocol, which kind of stands for Fast Reed-Solomon Interactive Oracle Proof. So that's a mouthful, and we'll unpack everything, and I think you're going to like this lecture. Okay, so let's start by quickly recalling what we did last time and how this would fit the picture. So, we talked about linearity testing. Well, we considered the class of all functions which are linear, and we want to distinguish whether some given function is linear or far from linear just by looking at local constraints, just by evaluating it at maybe 3 locations. And we then did the same thing with respect to the low degree testing. Well, we just look at a function and we want to know whether this is a function that can be represented as a polynomial of some bounded degree d. And when we said that, there is a context to why we looked at these 2 things, and we had a motivation. And the motivation was, we started with PCPs, probabilistically checkable proofs, which is proofs that we'd like to be able to verify locally and only probe them at a small number of locations. And we said that in order for such magic to happen, we need to, get a rich structure. And the rich structure is exactly the rich structure that we get from, linear functions and from low-degree polynomials. And in some sense, I want to mention a little bit about the coding theoretic perspective because it would become more and more relevant. So let me just annotate a little bit something. So when we discuss linearity testing, we were actually referring implicitly to the Hadamard code. And what is the Hadamard code? You want to take some piece of information. Maybe it's a proof that a graph is 3-colorable. Maybe it's just anything that we would like to communicate. And then what we do, we represent that information by looking at the message, like the information that we want to encode, and taking its linear, its multilinear extension. Or alternatively, we can think about, looking at our messages like the coefficients of some linear function, which we can then evaluate on some huge domain. So this means that we can take information and turn it into some, a code word, which is a big linear function. And that would add this nice local to global structure and things along these lines. And the Hadamard code is fantastic. It is, it is extremely local in the sense that we can use just 3 queries to know whether we're valid or not, and all of these nice things. But the blow up, the amount of redundancy that we're paying in that encoding. So let me kind of just remind the coding theoretic perspective. So if we look at the bottom right part, we take some arbitrary data, and it might be in some small domain, and then we make it far larger domain, such that we'll have this distance and nice properties. But this redundancy could be a big issue, and indeed in the Hadamard code, it is something which it's an exponential redundancy. So we also looked at the low degree polynomials, which constitute what we call the Reed-Muller code. And the Reed-Muller code, again, you can think about some information that you want to encode. Think about it as some vector. And then suppose you want your vector to be 0, 1, 0, 1, 0, 1. So these 0s and 1 could be the coefficients of a certain polynomial, which we can then evaluate over some finite field. Yeah. And this is the Reed-Muller code. And we saw that we also have a very efficient low-degree test for that. And today we'll see the last code that we'll talk about in this course. And it is a surprising one. So So we'll get right into it. And I see a question by Amit asking when I'm saying 3 queries, it's with huge soundness error. So actually, okay, it depends. So 3 queries for testing the Hadamard code, it would give us, not an amazing, it would probably something, it depends on the distance that we have, but, for constant distance, we can kind of think about, soundness of 1/10. So we'd like to repeat it maybe, from 3 to 30 times. But when we'll actually build PCPs, we'll see that using all these low degree polynomials and stuff and the structure that we can kind of take curves and send manifolds and all of that jazz, we'll actually have a PCP where we truly make just 3 queries. And there are actually constructions where you only make 2 queries. So that you literally probe the object in these many places. Okay.
I have a question.
Yes.
So usually we quantify soundness error in terms of some security parameter, like we want to be negligible in lambda security soundness error. So would you be making queries which are polynomial in lambda, or is it really some constant which is independent of that security parameter?
No. So, okay, there's always a dependency. So when I'm saying the PCP theorem, which we'll state later, we will make 3 queries and we will be correct with probability 2/3. So then if you want these 2/3 to be something better, you can repeat it. And you can make it as small as you'd like by just like repeating the test over and over again. And so the dependency would be, just like Chernoff bound of like starting with, you have probability of error, which is 1/3, and you can, repeat it, and the tail bounds is exponential. So, if you want to have error which is 1/n, then you have to repeat it log time. If you want to have error which is exponential, then you need to repeat it n times. But the main setting which we care about is, some arbitrary, that the probability of mistake would be some small constant. And then it means that we only need to repeat it constant number of times.
Okay, thanks.
Sure. Okay. So today we're going to talk about the Reed-Solomon code. And the Reed-Solomon code is actually quite, simple. It is just all polynomials, univariate polynomials of degree at most d. So in fact, maybe the only thing which could surprise you here, which is like the set of all polynomials of degree at most d, is that rather than writing the function from f to f, I'm writing it from some subset L. But the point is that we can just like choose whether we want to evaluate the function over the entire field, or maybe we want to evaluate it over subsets of the field. And you'll see exactly why I want to have this additional flexibility. It would be, we will be able to, sometimes you have a field, and maybe you want to remove some elements so you have a nice property. For example, if you have a finite field, a prime field, you can remove the 0 element, and then you have a multiplicative subgroup. So sometimes we want to consider part of the domain. Okay, so that's that. And also this is a good time to kind of mention a notation which is not really important, but you don't really have to make a distinction, but it could be nice. I mean, you can notice that on here, I have a function with no hat, and here I have a function with hat. And what do I mean by that is just, there is a distinction between a polynomial and, oh, I see that, and also this is a question that Tal asked, so thanks. So, so a polynomial could be a formal object, just, linear combination of coefficients, but a polynomial could also be a polynomial function, which is the function that we get by evaluating the polynomial. So when I'm writing f hat, I'm literally thinking about an abstract polynomial. And so, to probe this polynomial would be to look at its coefficients. And when I'm looking at the function without the hat, I just look at, a long vector of evaluation, just like a list of the values of the function at each point. So it doesn't really matter, but it could be a little reminder, like help, just to annotate and help. Okay, and kind of like the picture that we should have with univariate polynomials is that we have this degree of freedom. We fix d+1 points, and that determines an entire polynomial in a unique way. Okay, so what do we know about the Reed-Solomon code? So we have locality which is O of D. And that I mean, it's enough to ask O of D many queries, and using that we can test whether an arbitrary function is low degree polynomial or not. And here I'm writing that this is with respect to dimension D plus 1. So you might ask, what do I mean by dimension D plus 1? So let me try to clarify. First of all, this D plus 1 is kind of like the amount of information that we encode. So suppose that what I want to do is I want to start with some 3 coloring of a graph. And then I want to, so I write it down on a piece of paper. And now I want to endow it with this nice symmetry and a nice structure. So I encode this function, this coloring, by a low degree polynomial. So what does it mean? It means that I took the coloring, I wrote it over some arbitrary D plus 1 points, and then I'm giving the evaluation of this polynomial not only on this D plus 1 points, but on a very large domain. So that's the way I encode it. But then what does it mean? It means that if I started with data, which is of size D, then the locality, in order that I can verify that the data that is properly encoded, is also D. So it's linear in the size of the object. So in some sense, I have to read the entire information in order to verify that something behaves nicely. So if this is the case, then why should we even look at the Reed-Solomon code? And why not, do all the hard work that we did last time and look at the Reed-Muller code? So we call it the Reed-Muller code is exactly like Reed-Solomon, but in more variables. So instead of a univariate polynomial, the only thing that changes is that we have, n variables. Now this polynomial is over L to the n. And this kind of admitted this rich structure that they went on and on about yesterday, about the lines and the planes and all of that stuff, with the nice property that, if the locality is O of D, even though the dimension is O of D to the n. So what do I mean by that? So here, if I'm writing the information, I'm writing D to the n. Like, for example, I can write down, maybe it would be nicer if I just do, sorry. Okay, so suppose that, just for concreteness, let me instantiate this. So suppose I'm choosing D to be log of m for some parameter m, and I'm choosing n to be log of m over log m. I mean, you might ask, why did I choose this weird thing? It's just because if I do that, then when I write D to the n, then I get exactly m. So what does it mean? It means that I can have dimension of m. I can write my information with m. So for example, I can write the colors of m vertices of the graph, but then the locality would be log m. So the locality is exponential in the size of the data that I'm encoding. Okay, but it's just parameterization. You shouldn't worry about it too much. And yeah, and by the way, just as an aside, the reason why I'm saying dimension is because if I'm looking at the set of all low degree polynomials to degree most b, then this would be the degree of the subspace that's the induce. But anyway, that's an aside. Okay, so I know I kind of already by accident showed it on the screen, but can anyone tell me why? Why would I possibly want to use Reed-Solomon instead of Reed-Muller? Okay, so there is a question regarding easier testing, and in fact, we'll see that it's actually much harder to test them. So it's in the other direction, and the key point is this redundancy that I mentioned. It's how much more information we need, how much redundancy we add to get this structure. So for example, In the Hadamard code world, we get locality of 3. This is like amazing, but we pay by encoding data with an exponential amount of like extra bits that we need to represent. With Reed-Muller, we get a polynomial redundancy. And the nice thing about Reed-Solomon is that the dependency is linear. So now, for example, for those who ask regarding blockchains and stuff like that, suppose I want to have a proof, a proof sending me a proof, and I want it to be something which is short enough that I can put it on a blockchain, then size really, really matters. And so we don't want the site to kind of blow, as in Reed-Muller, to some polynomial. We want to keep it as minimal as possible. And Reed-Solomon, in fact, as a code word, it has the property that it has the best possible rate with respect to the distance and what we need. And that's exactly what Ida wrote in the chat. And in fact, that's that it gives us the best trade-off of distance and rate, the redundancy versus distance. Okay, so I see a question in the chat just to explain again regarding the difference between f and f hat. So just to say, f is a function. You can think about it as list of values, like just a vector where you say f evaluated 1, f evaluated 2, f evaluated 3, so on and so forth. And f hat is a formal polynomial. So, ax plus bx squared, and so forth. Okay, so that's the Reed-Solomon code, and hopefully this gives some idea of why we want to consider it. So let me state the problem that we want to do. So we want to find this proximity test, this property testing for Reed-Solomon. So what does it mean? We want that if somebody gives us a valid code word, we'll accept with probability 1. And if somebody is giving us something which is far from a valid code word, then we'll reject it with probability, which is, close to that distance. For example, a good thing to say is if we have a function which is, constant far, maybe 1/10 far from Reed-Solomon, then we'll reject with some constant probability. And I think that by now you're probably well versed in this formulation, so we can see this picture where you want to accept things in Reed-Solomon and want to reject things which are far from it. Okay, but what have we already seen? So we know that using D+2 queries, we can get a nice test just by querying D+1 points and then another random point and interpolating and checking for consistency. But we also know that D+2 queries are necessary in order to achieve any decent soundness. And the reason why is because, think about it, if you take D+1 points, then any value of D+1 points can be is the low degree polynomial of degree D+2. You can always, there'll always exist a polynomial of degree D, which has D+1 points wherever we query it. So, anything that we'll see will look to us as a low degree polynomial unless we reach this threshold of looking at D+2 points. So, in some sense, you might say, what am I going on about here, right? I mean, sure, we want to do something with Reed-Solomon, but we have, a test which is tied to the single query. So what is the left to be done here? So just to mention, not to say that Reed-Solomon is not interesting in, if we can evaluate Reed-Solomon on a very large field, then this might be interesting. But in our setting, when we want to be very tight and we don't want to incur redundancy, then we really need the query complexity to be, much, much, much less than D, hopefully exponentially less than D. So what do we do? And the answer would be to kind of say, well, this is a limitation for classical, property testing algorithms, but maybe we can, augment the model with more power, and then we'll be able to do it. Now, if you think about it, we want to use this test as a part of a PCP, as a part of a proof system, as a part of something of this sort. So it makes sense to use the help of a prover. Okay, so this is where we introduce this notion of interactive oracle proofs, which it's quite a beautiful notion. And I'll just say it first in words, and then we can like define what's going on. So, we start first to remember that when we say what is an NP proof, we have a prover, or we know it's an existence of a proof, and the proof is being given as one linear, like one object to a verifier, and the verifier reads the entire thing and checks the problem. And we also saw two extensions of that. One of them is an interactive proof, where prover and verifier are kind of like talking to each other, and the notion of PCP, where we have a prover that sends a long proof, and the verifier only probes it, say, at 3 locations or something like that. So an interactive oracle proof is exactly the love child of both of these models. So it's an interactive proof system where the prover is sending a PCP at each stage, right? So a nice way of thinking about it is as just like a multi-round PCP. So what will happen? We have the prover, it sends a PCP, then the verifier maybe say, I want to know something about this and that, so it sends another PCP and another PCP and another PCP. Okay, so now, just to give a bit of context, this is actually quite interesting how this notion was born. Like, if you ask me, I think this is an extremely natural generalization to consider. But this was actually originated simultaneously in 2 different works for completely different reasons. One of these works was by Reingold, Rotblum, and Rotblum, and they were interested in making, just like taking Shamir's protocol, which you covered just like yesterday, and making it with constant rounds. And this was an important notion to get that. And on the other hand, we had Ben Sasson, Chiesa, and Spooner, 2 of which are part of this summer school, which kind of like ask themselves, what is the most general setting of a proof system which we can compile into a cryptographic proof, a snark or something like that? And we'll see how to do that later on this course. But so as to say, I think that this notion is both naturally appealing and well motivated by applications to complexity theory and application to real life delegation of computation. Okay.
I have a question.
Yes.
So it seems that giving the power of interaction would help the malicious prover more than it helps the honest verifier. So do you have any intuition on why this model of proofs like IOPs will help us capture more than what PCP cannot already capture?
That's a good question, and it's a tricky one, right? Because whenever one is augmenting the power of the prover, whenever you increase the power of the prover, you do 2 things. You help the prover do good, but you also help the prover do bad. And it's often the question, we see it a lot in the quantum setting, where you're kind of like saying, I have a proof system with a classical verifier and a classical prover, and then you make the prover quantum. So you ask, well, did I make the prover now, can now the prover do amazing, beautiful things he couldn't do before? Or maybe that also just like allows him to use more cheating strategies and do things of this sort. And it really depends on the specific case. Like, for example, if I'm going back to the, MIP star setting, so this is like a setting where you take some multi-prover interactive proof, and by telling the provers quantum, even though it was unclear for almost 2 decades, it ended up being, making the whole system incredibly powerful. So it's hard to predict. And also, I think that Shafiq's comment, who said that like the power over PCPs lies in the fact that the prover doesn't have to commit to the entire PCP beforehand. That's a good like intuition for that, because in some sense you see how the protocols also work. You're able to do some commitment, and instead of like providing the entire tree of interaction, which is what you have to do in a PCP. you can give it time after time. And this is also a good place to say that this whole notion, the protocol that we're going to see, it's actually an improved version of the work, not improved, of a generalized version of the work by Ben-Sasson and Sudan from 2008, who did the same idea in the setting of PCPs with no interaction, and it just like leads to a very different kind of thing. So these things are quite related. Okay, so what would be, this type of proximity proof that we need to have in that setting? So we want to have this, IOP, and we want to say we solve a property testing problem with it. So the IOP, we have the prover and the verifier, and they talk with each other. And then we want to say that if we have a code word which is valid, we'll accept with probability 1. And if it is delta file, then we reject with probability, which is, something like delta. And so it would look something like that. So what's happening here? Let me kind of highlight it a bit. So we have the prover and the verifier. And the verifier sends some maybe message, and it gets a PCP, it sends another message, gets another PCP, and so on and so forth. But then we also have this function that we want to actually test, and we'll make queries to that function and try to deduce information about it. Okay, so what we're going to show is the following theorem, and it looks like, there's so many parameters floating by. So I want to start by just like looking at the most important part, and the rest of them are nice to know, but it's not crucial. So what I want to say here is that we have a theorem that you can take the Reed-Solomon code word, and you can test it using a proof of length which is linear and queries which are logarithmic, right? I'll unpack the rest of the parameters in a second, but the main point, the main message to take, if we want to test the Reed-Solomon problem, we need to make D queries. But if you allow us a proof of linear size, then instead of D queries, we can make just log D queries. So so that's an improvement. And as for whether we can make queries to previous round PCPs, then it really depends on the particular definition of the model. But for us, we can allow it, and it would still be okay. And I'm not sure regarding the comment about an honest verifier. I'm not even sure what an honest verifier means in this setting, because the prover might be malicious, the verifier just try to get. Okay, so I see that. Okay, so I see a lot of questions, so I'll take them one at a time. So let's start by unpacking the full theorem, and also mention what I mean by smooth domain. So we said for any finite field F and some subset of it L, which is smooth. So what is smooth? So it's a technical condition which you see all the time in fast Fourier transform, and then you'll see that it's all connected to that. Namely, what it means is that you take some, multiplicative subgroup. So you take some cyclic subgroup of order which is, 2 to the k. So roughly, what does that mean? It means that, like, for example, if I take F and I remove 0, then I have this nice multiplicative subgroup. And I just want this subgroup to be, something which plays nicely with bits. So I want it like to be size 2 to the k. And I just want to mention that maybe to say how much this is like a live field. So just a few days ago, there was a paper which, like in 2 parts, which I think that this restriction is about to be completely lifted. The paper is not out yet, but I didn't get to read it, so I don't know all the details. But I think that this constraint can be removed. But that's some new work. And to go over the rest of the parameters, it would mean that we won't have any error in the completeness. So we just accept with probability 1. The rejection would be, roughly, if you're 1/10 far, then you reject this probability, 1 minus 1/10. The number of rounds would be logarithmic. The prover will run in linear time. The verifier will run in logarithmic time. And the randomness complexity would be logarithmic. So all the parameters like as tight and as nice as we can pretty much hope. Okay, so that's the theorem that we see. Let me quickly skim if there are any questions. I think that no, but feel free to unmute if you have anything to ask.
So I don't know if you answered this question already, but there was a question about whether or not you could make multiple queries to the previous rounds, PCPs. And then somebody said you cannot, and then that would assume like that the verifier doesn't do that, right?
So no, so we will allow that. I mean, there is no like you can think about like the PCP as being the verifier holds it to this point, and it can make queries. So it's totally fine. I mean, one could also define it a bit differently, but this is I think the most natural definition, and it definitely works for us. Okay. So this is going to be called. So we'll call this protocol the FRI protocol, the Fast Reed-Solomon IOP. And in fact, this protocol is being implemented in practice for zero-knowledge snarks, and it's actually being used, as we speak, running on system in deployed systems. So it kind of goes beyond theory. So
one question.
Yes.
So what is the difference between the first message, which is like a function f, and then the proofs that precede it?
No. So the first message. So the first message, the verifier is just like sending, maybe randomness, maybe something along this line, and then gets some PCPs. But there is also the functions to which we are allowed to make queries.
I see. Okay. Yeah.
Okay. So let me continue. And this is maybe it's like really important, like it would be useful. So I asked you to look at a video, kind of go back and revise a bit the notion of fast Fourier transform. So this is a non-mandatory 5-minute discussion that we have regarding the intuition for this algorithm, which is heavily inspired from the fast Fourier transform algorithm. So if you feel comfortable with FFTs, then this could really help you to kind of like see how people came up with this algorithm. And if not, then feel free to go grab yourself coffee, and in 2 or 3 minutes we'll get back into the actual details. So you won't need this is only for intuition. So okay, there's a cool idea in fast Fourier transform, where we can take some polynomial of our choice, and we can kind of divide it into odd and even variables. So for example, what do I mean by that? You can maybe, what happened? Not what I wanted. Okay, sorry for that. Okay, so you have this x5 plus 3x4 plus 2x squared plus 5x plus 7. So you can always naively just group it into something which is 3 of x to the 4 plus 2 of x squared plus 7. And then here do this x5 plus 5x. And then what you can do is you can take x squared out of it, of both of these terms, and just write it in these terms. So all we did here is just like partitioned a polynomial into an odd part and an even part. Now you might want to ask, why would we want to do that? And the reason will become clear in a second. So what does the FFT protocol, the algorithm does? Well, it computes the Fourier transform, but an important part of it, which is the main technical content of it, is to be able to evaluate a polynomial. And notice that this polynomial here, I'm writing it with a hat. So we have a polynomial that we get by the list of coefficients, and we want to evaluate it. So we want to move from the coefficient representation into the truth table representation. And how do we do that? We want to, evaluate it on some domain L. So first of all, maybe one thing to say, typically we want to do it on some set that we choose, but we're thinking about the complex number, but here we look at a more abstract setting where it is any, cyclic group over some smooth field. Okay. So what do? We evaluate, we do this partitioning to even and odd, and we evaluate the polynomial of the even part, we evaluate the polynomial of the odd part, and then we have this, nasty looking equation, which essentially just tells us that we can reconstruct the function according to this rule. Well, the important part, and the reason why we did that, is because we want to save half the queries. So what do I mean by that? So the nice thing is when you divide into odd and to even and odd coefficients, is that we can now talk about, rather than talking about, things from L, we're talking about things from L squared. So the coefficients, like the function that we get, is a function which take x squared as an argument. And why is that nice? Because, if you think about x squared and you want to evaluate it over, some domain, then if you know the value of at x, because it's squared, you also know the value at minus. And so it means that what you do, and this is what's happening here, is that you evaluate the even part only on points of the form x squared, and you do the same for the odd part. And then one time you compute the value of the function, with respect to w, and the other time you use the same values that you computed before to compute also the value at minus. And you might say, well, fine, so we just made the thing just half the points, but we can also recurse on this idea because we have this structure of L squared, L to the fourth, and so forth. So we can recurse and recurse and recurse, and this can make the whole thing if we do logarithmically many steps of the recursion, and this would turn the complexity, which is typically L squared, into L log L. Right, so instead of evaluating each time the polynomial, this takes you L, and then instead of doing it to evaluate L points, instead of evaluating L times the time it takes you to evaluate, which is also L, you can just do it L times log, because we recursed on it and we made the problem smaller by a factor of half each time. Okay, that's the only thing you need to know about the fast Fourier transform. And the reason why I showed you that is because that's, I think, the only new idea, or not the only new idea, but it's the most creative idea we need to do in order to get this IOP for testing Reed-Solomon. So what we'll do is we'll try to take that exact idea and apply it to low degree testing. Right? So what do I mean here? So we have
I have a question.
Yes, please.
So why are we evaluating on the entire domain L instead of just d many points? Because the degree of this polynomial is d, so it should be sufficient to evaluate at d many points, right?
Yeah, but so when I'm talking about, absolutely valid point. But when I'm talking about the fast Fourier transform, this is not we don't think about queries and we don't think of anything of this sort. We just we literally have a Turing machine which gets a polynomial by its list of coefficients, and we want to evaluate it on certain points. And so to evaluate it to one point, you have to kind of plug it and evaluate the coefficients and do the multiplications and do the whole kind of thing. So it is. One has to be careful that we are moving here from setting, FFTs just for polynomial time algorithms, and here we're doing this type of locality and query-based things. But thanks for that question. So let's just say how we can use such an idea in order to do low degree testing. So we can take some function f, And maybe this function has degree at most d, and we can break it into two functions, like the even part and the odd part, and these functions would have degree d over 2. And so maybe we can take this simple idea and recurse and recurse and recurse and get something, right? So hopefully that gives you some sense of the approach that we're going to do. And what we'll do now is we'll try to rediscover the FRI protocol, as opposed to just like, I'm not going to show it to you just yet, but we'll do it step by step. So first thing, just musing, right? I always, when I'm reading a paper, I try to ask myself, how did they come up with it? So for example, how did someone think to use fast Fourier transform in order to test Reed-Solomon code words? So here's my 2 reasons that I came up while I was trying to explain it to myself. One of them, it's kind of like an exhaustive reason. I think there's quite a famous quote due to Rota that says that every mathematician has just a small number of tricks which he or she ends up doing using a lot of times, and we don't have that many algorithmic tricks regarding univariate polynomials. The structure is too loose. So whenever you think about univariate polynomials, one of the first ideas is the fast Fourier transform. So that's one type of idea. And the other thing is that similar tricks have been used in the literature before. So even if an idea seems completely mind-boggling if you see it for the first time, it's important to remember that most papers, even if they look super complicated, typically there's a line of work. And there's each paper added 1 or 2 nice ideas. And if you just see the top of the culmination of 20 papers, then the total amount of ideas look overwhelming, but in fact it tends to be just baby steps. And it's important to keep it in mind while we're doing research. Okay, but suppose that we have this idea. I want to convince you that we can come up in half an hour with the FRI protocol just by trying the most basic things and failing and correcting. So, and one thing that I forgot to mention, that notice that I will, for convenience, will look at functions which are strictly less than d. So instead of testing if it's d or equal to d or less, we'll just focus on d. It would make our life with less notation. Okay, so now let's do low degree testing with that. So here is the most naive approach. Can anyone suggest how a protocol between a prover and a verifier might look like in this setting? So I have a polynomial, and I kind of want to split it into 2 parts and recurse. Any suggestions, ideas how we can start? Whenever I'm asking you a question, just an excuse for me to speak off.
A random linear combination again?
Okay, so that's you're taking the next step. So I want to start with something, absolutely fantastic idea, but I want to start with something even simpler, what I would have done, it's first step. I'd say, we have this function f that we want to test whether it's of degree d. So let's, ask the prover to compute this, the prover is all powerful or whatever, so at first we don't really even worry about it. So we kind of computes the even part, computes the odd part, and then it takes these polynomials which it computed, okay, and it evaluates them over L squared, so with respect to this x squared, and just send the thing to the verifier, right? I mean, now the verifier, what does it have to do? Essentially 2 things. The first thing is to check that these functions actually correspond to something. The prover can send, just completely arbitrary function, but we want to check that these are the functions that are consistent with the protocol. So we'll take G and take H, and we'll combine them. We'll combine the even and odd parts in the natural way, and check at a random point that they agree with the function. So we make one query to our function, and like this one query to each one of these polynomials that the prover is sending. And this is all like really nice and well. And what we can do is say, well, let's just do it. Let's recurse over this idea. And each time we take a big problem, we make it into 2 smaller problems, and we recurse on that and try to solve that. So why aren't we done? Why aren't we happy here?
Because it will explode. Like we're gonna have to check too many things.
Very good, very good. So indeed, this would lead to a linear number of queries. And why is that? The whole idea in recursion is that we take a big problem, we split it into 2, and then we focus on one part. If we take a problem, we split it into 2, and then we focus on both parts, and then we're doing essentially nothing. We just like have a tree and we check everything with that tree. So that's a real bummer. And to make it even worse, even if we're doing that and we don't care about and we want to do linear number of queries, which makes it completely degenerate and not interesting, even then we might be mistaken. How is that even possible? So there's an important phenomenon that happens here, and I kind of like try to show you. It's called distance decay. And the point is kind of like, maybe we had the functions, and the functions, we had started with this function which is very far from having from being low degree, and then we decompose it into two smaller problems, and each one of them was far, but maybe just a little bit less. And when we do it over and over and over and over, they would suddenly get closer and closer and closer to low degree, and maybe entire low degree. So let me show you how this could actually happen. So think about the following diagram, and I want to spend a bit just like meditating on it. So what is happening here is we have the function f. Think about it as a function that we evaluate over, the entire L. Or we can think about it maybe as, both positive numbers and negative numbers. And then we break it into this like odd and even of L squared. So each point, each point of f, it's being affected by twice by g. You can think about the left-hand side of f as like the negative part, and the right-hand side of the positive side. So, if you look at g, it contributes one thing to f, and one to the negative side, and 1 point to the positive side. So what does this tell us? Suppose we had this function, and maybe it has 40% far from being a valid low degree polynomial. Then we're breaking it into these 2 functions. But because the function g would contribute twice to f, it could be the case that g would be 20% and h would be 20% far. Together it would be 20. It would consist this like 40% of problems of errors, but we then recurse on each one of these things, and the distance decayed by a factor of half. And so if we do this, the distance will decay by a factor of half and half and half and half, and then in the end we have nothing. So that's not what we want to have. And even worse, I can show you a concrete example where the distance decay, even if there is no errors at all. So what do I mean by that? And think about it, it's like a really simple kind of thing. So granted, the errors here are a bit confusing, but think about a code word, which is, just a block of 1, and then a block of zeros and ones and zeros and ones and zeros, and then a -1 and a 0. So we are combining these 2 things together. So it could be the case that we take ones and -1s, and when we're merging them, they'll kind of cancel each other out, right? So the problem that when we take this type of information and we say that each point is being derived by putting together and adding 2 other points, then we can have these annoying cancellations. Now, keep in mind, this is just to give you an intuition. We're going to do it, over the next slide in formally. So if you don't see exactly how this folding happens, though, it will become clear in a minute. Okay, so distance can, drop and drop and drop until it reaches essentially nothing. Okay. So now we want to do something better. And this could be something that, and something better is what Matthias suggested. I mean, what's our main problem here? We have this recursion tree, and we take the problem and we split it into two, but now we want to kind of, we don't want to go and explore all branches of the tree. So maybe we can combine them together. So what do I mean by that? That would be attempt number 2 out of 3 attempts.
I have a question.
Yes, please.
Why is that distance decay a problem?
So that's an important question and thing to. So suppose that we want to test a function that is whether it is far from having low degree. So we reduce the problem by each round of interaction into checking some other problem of low degree. So if at first we started, 40% far from being low degree, then there is some probability that we can kind of like catch it. But then we reduce the problem to something which is 20% far, and then 1% far, and then 0.1111 far. And at the end, we can actually get something which is actually of low degree. And then we've lost. So if we want to recurse, we have to maintain that in each stage of the protocol, we maintain this level of distance. So if we start at 40% far, then in all steps we'll be 40% far.
I see. One more question. So suppose this distance decay was not a problem, then we have this problem of linear number of queries, right?
Yes.
Is it possible to select just the random path in the tree? So out of these two, G and H, the verifier will check for a random one, either G or H. And then in the next claim, it will select either one of those two claims.
So that's another natural approach. It's one which actually doesn't work, but it's not trivial or immediate to see why. But we actually will see that as part of the analysis of the case of work. But it's a very natural attempt.
Right. Okay.
Good. Thank you. So let's see the second approach here. So the second approach, I want to start, before I kind of like presenting, I just want to say, here is an idea. So we have this G and we have this F. And now we want to, to check them. So maybe, let me just like try to my best at drawing. So we have this like G function, and these are the good places, but we have some errors here and here. These are the places which are not corresponding to a low degree polynomial. And we have this function H, and maybe, we have some errors here and maybe some here. So here's a natural approach, well, we kind of like, and so this would be, maybe 20%, 20%, and we want to have 40% as we started with. So a natural thing to do, which is what like I would have suggested in such a situation, would be, well, let's just take G plus H. You take these vectors, you add them together, and then, you have the problems here, and you have this thing, and you have this thing, and this thing, right? So it's a nice way. So maybe to make it even more concrete, think about the code word being, I can't erase, I can only undo. Okay, so, oh no. Yeah, okay. So think about the code word like being the all zero code word. So, it's like 0, 0, 0, 0, and then we have 1, and then 0, 0, 0, 0, and then 7, right? And when we have here H, then we'll maybe have here 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. So when we'll add this thing, we just get this the summation G plus H, it would just be this 1, 1, 1, 7. So this is all nice and well, but there's a problem with that. can you tell me like why just like taking G plus H in this way might not preserve the number of bad points?
Like a 1 and a -1 cancel.
Absolutely, exactly that. It's because like imagine that if here instead of 0 we had a -1, and then we add them together, so we get here 0. And in fact, it might be the case that we are extremely unfortunate, and then everything cancels, and so this is a bad idea. But in some sense, it feels that and we had that before, also in low degree testing, that you kind of like try this idea and it almost works, but there is this annoying thing. So you add some randomness to not get into this local minima, and this is exactly what we'll do. So after this, long discussion, what we'll do is that we let the verifier sample some random element and send this random element to the prover, and then instead of sending, G plus H, we'll send a linear combination of them, G plus alpha H. And what's the intuition here? The intuition is if we happen to be in this like 1 plus -1, then because we are taking this -1 and we're sending it to some a random element 17, then we wouldn't have this cancellation unless we are extremely unfortunate. I think and this like by some miracle we got there. And we analyze it, so you see that it does make sense. So what's the idea? So the prover is taking the function, it breaks it into these two parts, even and odd, and then it kind of like using randomness, it folds it into one smaller chunk and send this one smaller chunk. The verifier, first checks for consistency, and then it like recurs on the smaller part. And we recurse and we recurse and we recurse. Okay, so that's the idea. And I want to kind of like tell you roughly what will happen, and hopefully that that would make sense. Okay, so first of all, let's look at the number of queries that we'll make. So the number of queries is actually really good, right? Because we take a problem of size n, and then the prover sends us something, and then the problem becomes of size n/2, and then it becomes size n/4, and it just, so the number of queries will be logarithmic because after log iteration, everything will become of constant size, and you can just read the whole thing. And there's a question, why does this random folding make sense? Just to kind of like strengthen the intuition that I said. So let's first consider the case which is noise-free. So what I mean noise-free? Well, we don't have errors, and we get like these these polynomials which are fully consistent. So what does it mean? So in terms of completeness, I get you some polynomial of degree at most d. So when we break it into two parts, each one of the parts would be a degree of most d/2, and then when we take any random linear combination of them, then they would be of degree at most d/2, right? Like, I mean, they can't like suddenly, if you take two polynomials of degree d/2 and you put them together, the degree can't increase. It might cancel, there might be some cancellation, it would drop to be d/2 - 1, but it can never increase. So this is nice. And in terms of soundness, so suppose that the degree was greater than d, right? So suppose we get a fully valid polynomial of degree greater than d, then we know that either the odd part or the even part would be of degree at least d/2. And in this case, we'll get the following. We'll get that this is really ugly. So we'll get that the probability that the degree will drop is at most like 1 over the field size. So why is that? So think about what's happening here. So we have this g and we have h. So think about two polynomials. And if we combine two polynomials, in what case can the degree drop? Only if the largest two coefficients will cancel each other out, right? So we have two polynomials of degree d over 2, and we add them together. So only if the coefficient of, x to the power of n over 2 just happens to drop. But since we're choosing one of these functions times a random factor, then it means that there is only one field element that if we multiply by that field element, then this cancellation would happen. So this is exactly why we get this like 1 over f. So unless we happen to choose so there is only one alpha such that taking these two things would lead to cancellation, and only if we turn out to be extremely unlucky and chose it, the degree will drop. And so this is why the protocol kind of works. And okay, so let me just say go for a second again to the number of queries. Yes. Okay, so the number of queries, the idea to keep in mind is, we started with the problem, like we get the prover sent us these two polynomials, and we make 3 queries here just to check consistency. So this is, constant. And then we sample the element, we got the folded function, and we make this additional 3 queries. So in each round, we make constant many queries, namely 6. Right? Like we make 1 query to this thing, 1 to this one, 1 to this one, 1 to this one, and again to G and H, we're making 2 queries here. So 6 queries per round. And we do logarithmic many rounds for the distance to drop for the length to drop from n, n over 2, n over 4, n over 8, until it drops into something constant. Does this make sense?
I have a question regarding the smoothness. So the reason that the multiplicative group of the field is supposed to be smooth or has too high adicity is only for the prover, or that he can perform the FFT and evaluate the polynomials in quasi-linear time. Is that correct? So it's not about the verifier.
I mean, okay, so first of all, the constraint is not, it's constraint of the analysis and the construction, because there is now a newer constructions which avoid it. But what I'm kind of trying to we want to have this nice way of decomposing polynomials, which would admit this structure. I'm not entirely sure how the scheme would look like if the field does not allow for these nice cancellations. So I'm not sure I kind of see.
So that the splitting into even and odd would work independently of whether we have the domain is the group is smooth or not, or
but there is this hidden coset structure. I mean, you will get to see it when we'll get into the analysis. And I think let's try to keep an eye together and see if this is something which is only affecting the prover. I tend to think it should affect both the verifier, but we'll get to see it when we actually analyze the protocol, because there is, when we say folding, there's actually something deeper going on, and we'll get to it very explicitly. Thanks. And by the way, regarding the other question in the chat, where the form comes, it's just because I was not careful. We make 4 queries, not 6, because this query and this query we already made here and here. So it's just 1 query for each one of the functions. So thank you for that. Okay, good. So that was that. And now we want to consider the general case. What is the general case, which is noisy? It means that the prover doesn't have to send us, a polynomial which is of degree greater than d, but rather he can send whatever he likes, right? The prover can send maybe a polynomial of degree d or less than d, but with some noise, and maybe it's a function which is take your favorite polynomial of degree at most d, and then co-opt it at some places and change the values. So what will happen is we'll have the same kind of diagram where we say, each point of G is kind of constructing and responsible 2 places in F, and distance can kind of drop. However, this time, because we took a random linear combination, then what we'll show is that the distance will not, there will be no cancellation, and so when we fold them together, then we just like the distance will remain. And that's like the high level intuition, which remains to be shown formally. So it seems that folding solves the problem that we had, and it does. And there is still a question to be asked: what happens if the cheating prover decreases the distance by sending functions that are inconsistent, right? Like maybe it's like instead of like following the protocol, at some point it sends you some completely low degree function, but one which has absolutely nothing to do with the other functions we discussed, right? Like we started with this f, and then we fold, and then it sends us some low degree function which has nothing to do. Then can anyone tell me why this wouldn't be a problem? Exactly. And as Arkan is saying, this is exactly why we have the consistency checks. At each point, we're checking that all of the functions, kind of like the two parts of each function, can be reconstructed to give us the original function. So we check for consistency of the folding. Okay, good. And then if we kind of like try to quickly get an estimate of the probability that the protocol will fail, then at each round there is some chance that we will fail in a consistency check. Why? Because you could choose two low degree polynomials that agree on some points, but not on most of them, right? Like we can't agree everywhere. You can't switch from one function to the other, but we don't know, there can always be some chance that, we have this, like, we took a function f, we split it into some g and h, which at all have nothing to do with f, but maybe on a single point here and a single point there, they happen to agree with the folding. So we'll have that probability of mistake, and we will have it per round. So we'll have some small chance of error, and this will repeat every round. And because the number of rounds is logarithmic indeed, it's not just a constant, this means that the soundness will degrade. So we have two options. The first option would be to make more queries each round, like maybe we'll need to make log d queries each round. And if we make log d queries each round, we can make the probability that the consistency check will fail something which is sufficiently small, such that we can tolerate this log d many rounds, the union bound of this log d many rounds. And that's a perfectly valid solution. At this point, we can stop. Like if we are happy with having, more than a constant number of queries, if we're happy with having log d queries every round, then we can just stop at this point. We'll have, log d per round and total of log rounds, so we'll have log d squared, and everything would work nice, and one can even take this exact construction and analyze it and be like, and get a protocol. But in fact, one can do simple trick, like a small tweak of the protocols that we won't have to deal with that problem at all. Okay, so any questions while I'm skimming the chat? So I see already in the chat question regarding what if the errors are aligned and they fall in the same positions of g plus alpha h. So this can definitely happen, that things would be aligned, but that's where alpha is there to protect us. Because even if the errors are aligned at the same point, the only chance where they could cancel out is if they are exactly, a number and minus that number. And because, so suppose that you have this like 5, and then you have another value, which is -1. So if you happen to choose, to multiply by 5, then you can have 5 times -5, and this would cancel. But because we choose to multiply by a completely random element, there is only one bad option, 1 over f. So think about f as being a huge field, so 1 over f is tiny. So it's a very low probability event.
I have a question.
Yes.
So on the previous page.
Yeah, sorry, I'm just like put it. Yeah.
Yeah. So the check in blue that the verifier is doing f of alpha, whether f of alpha on mu square equals g of mu square plus alpha times h of mu square. So does this mu have to be same as the mu that was sampled in the previous phase?
So that's a fantastic question. In some sense, what you are alluding to is you're alluding to the solution. So in fact, it's a good question, and my next slide is designed to answer it. So let's like just show you the idea. So that's exactly the FRI protocol. So what is happening? It's just the following thing. So we'll take the protocol that we saw so far, and we'll just make two tiny changes to it. So the first change would be to kind of drop G and H, because we don't really need them. It's enough to have the function and just to send the folding. Like G and H were useful to us as kind of like as mental help, but in fact we can check the consistency of F and the folding of F, as opposed to say, we have F, we take it into two parts, and you'll see how this works. And the second one would be to make the multi-round consistency check, to have one consistency check which cross all rounds, right? Because like inherently, if we make a check which fails with some probability at each round, and we repeat it, then the error will blow up. But maybe we can make one check regarding all of the rounds, at all of the things at one time. Then we do it exactly as was asked. So first of all, just to make things a bit more concretely, what do I mean by this folding? So let's formally define it. So I'm defining, given some function f that I care about and some random folding element, we'll define to fold f using randomness alpha as follows. We'll have this term, which we'll see in a second corresponds to the even polynomial, and this part, which would be alpha times the odd part. Why is that? So, we'll show exactly why this is even plus odd. So it's a one-line proof. It essentially just tells us that, we're considering this element gamma squared from L squared. And we're saying, what does it actually mean to be the even part plus alpha the odd part? So the even part, we're getting contributions one time from the positive element and one time from the negative element, and this is divided by 2. Whereas and this correspond to the, to this type of picture. And in the odd setting, we'll have something which corresponds to this kind of picture when it's kind of like milled. So we'll have, this guy minus the minus value. And you might ask, why do I have here this factor of gamma? So if you remember when we do the Fourier, the FFT, so we have this like, odd, so we have, even plus x time odd. So this is exactly to compensate for that. Okay, so it's like something you can write down, and you can have, more detailed proof. You have a more detailed proof in the notes, but it's just a straightforward thing to check. And now if we do this change, we get the FRI protocol, which is, where we'll end for today. And the protocol goes as follows. So we have a prover, and we have a verifier, and we have the function f. So what will we do? So, the verifier will choose some randomness, some, just like flipping some coins, and we'll send the first random element alpha 0, which will correspond to the first folding. So in turn, the prover will say, okay, send me alpha 0. So I will take the function f, I will fold it into, I will think in my head about this g and h, and then I will bundle them together, g plus alpha 0 times h, and I will send this f1 back. So we send back the f1, and then the verifier chooses another random element and send it back to the prover. The prover takes the function f1, and now it folds that function. So it folds the folded function and send it back. And then, as you can imagine, this will repeat on and on and on. So, we'll do it, and then at the last round, the verifier will send yet another random field element, and the prover will fold, f of r minus 1 according to that element and send it back to the verifier. At this point, the prover kind of like no longer plays the game. It kind of like sends us all of these, PCP's oracle. It sends us all of these functions, f1, f2, f3, fr, and we'll make a small number of queries to these functions in order to verify everything. So what will we do? So we'll try to make a consistency check. So whether before, in each round, we chose a mu and made a consistency check, now we choose just a single mu, and we'll check it on all of the functions. So how do we do that? So we start with the first function, and we're checking, does this folding satisfy the fold formula, right? This is like just how we define the formula. So we just like check it with respect to mu squared, right? So we took this polynomial, we divided it into two polynomials in mu squared, and then we just check their relationship. But then at the next step, we have a function which is defined over L4, and we'll just take the same element mu, we'll square it to get mu to the 4, and then we'll do the same check with respect to that squared element. And we'll do that on and on and on and on and on. So instead of having a fresh mu for each function, we'll check all of them in a correlated way using elements which have this shared structure. So, and then the last function that we get, we need to just like check that it's of low degree, but because we did it for log time and each time we cut the size by a factor of half, this is like something, we can just read the entire thing because it's of constant size. So, and maybe this is not enough to get the soundness that we want, so we can repeat this whole thing several times. So we can just like choose, several of these mu's, but each time we check all of the mu's with respect to everything. So kind of to show the query pattern, it's a biased pattern. So what do I mean? We look at mu and minus mu, and then for the next step, this already dictates mu squared, and we'll have minus mu squared, and so on and so forth. So that's the whole idea of the protocol. And now, this was a high-level intuition. And what we'll do tomorrow is we'll get to actually analyze this protocol and see why it works and how everything kind of falls into place. And let's first start with completeness, because the completeness is as always, nearly trivial. It's just a way to refresh our memory of what is happening. So the claim would be that this protocol, the FRI protocol, has perfect completeness. And that's told by construction, because suppose that the function that we have f has degree at most d, the degree less than d. So fix any choice of randomness, it doesn't really matter. And then we know that, for each one of them, when we consider like the fold, when we consider like taking a function to be even plus alpha times odd, if the function since the function had degree at most d, then both of the sub-functions would have degree d over 2, or it depends on the round. If it's like on the first one, it would be d over 2. If it's the second one, it would be d over 4. So it would be d over 2 to the I, depends on the round. So the degree will drop by half each time we fold. If we fold at I time, the degree would be d over I. And then we're saying, well, FI, it's folding because, well, precisely it satisfies this equation that made us define the whole thing. And then we know that the consistency tests that we're checking, like these things that we check, will always hold because everything is, we just like check everything according to the plan. And the resulting polynomial when we folded and folded and folded would be something which is really of this tiny degree, and also of a tiny domain that we can read the entire thing, and everything will go nicely. So this was perhaps a bit wordy way of saying that the protocol is designed in a nonsensical way. Like it just makes sense. But maybe the interesting thing to check here is like, what is the complexity of the protocol? So the running time of the prover, well, it needs to generate this folding. So what is this folding? It's just like, taking one function plus other function and evaluating it. So the first size, it would be O(L), the first one, because the size of the function is L, the domain of the function. Second time, the domain is size L/2, so it's like plus L/2 plus L/4, and until it's like we take the entire exponential series, and it's still O(L). The verifier time would be the number of randomness that we need, which is like nothing, and we'll have this like L, which is divided by 2 to the randomness, is what we check at the end. So it's, the time that we run at the end is just O of log D, so all behaves nicely. And the query complexity that we're making is exactly what we had before, right? Like we make these consistency checks at each point, plus the chunk that we're reading at the end with the last polynomial. So that's the completeness and the running time. Hopefully there is nothing, it's fairly straightforward. And in terms of soundness, this is what, that's like the meat of what's left to be done. So first of all, I want to kind of like shout out to the recitation. So in the next recitation, you'll see like an attack on the FRI protocol. So what do I mean by that? You'll see what is in fact, in a sense, the best thing that a cheater prover can do in order to fool you. So so no protocol, randomized protocol, can be perfectly safe. There's always this small probability event that something goes wrong in the protocol. And what you'll do in the recitations, you'll see what is like arguably the best, or what we suspect to be the best strategy that the prover can do in order to maximize the chance of fooling us. But we'll see that the best attack actually gets something which is kind of cool. This is not a proof, but rather what we do is we show that there is one particular attack that gets something. This means that the soundness cannot be better than that. And then to show soundness analysis, we need to show that nothing, no attack whatsoever could do much better than that. And what we'll see is an upper bound, which is up to a first order, quite good. We'll get this bound. So it's almost exactly what you see here, only instead of 1 over f, we'll have L over f. And instead of like 1 minus delta, we'll have 1 minus either delta or some constant that we'll need to deal with. But but it's fairly close. The constant, it's just like a universal constant. You don't really have to worry about it. And we will show this thing. And just to say that the proof itself, I mean, at this point, we could have just stopped and say, well, you have some intuition of the protocol. But I think that the proof has some really nice fundamental mathematical statements regarding, worst case to average case distances between general linear subspaces. This is like an interesting question that one can always ask. Suppose I have 2 linear subspaces, and I have one point that is, delta far from one subspace to the other. What does it mean that, and what would be the average distance of a point from the subspace? And we see that this is like a fantastically interesting phenomenon of linear subspaces, that if one point is far, like if you have 2 subspaces and one point is far from the subspace, then in some sense, almost all of the points must be far. So it means that linear subspaces are kind of like cannot behave, like this. But you see what I mean? And also just like to mention that like when trying to improve on the soundness, there are actually better bounds, and they are using quite beautiful deep mathematical tools, many of them coming from like algebraic geometry and algebraic function fields. And so if like me you're a big fan of the Riemann-Roch theorem, then you can have a lot of fun and use some pretty nice math while doing so. And just to mention that getting a tight analysis of the soundness, it is something which is like quite an exciting open problem with important implications both in theory and practice. So that's all I wanted to say for today. I'll stop the recording now.